We have from each one of the main engines, from each of the three main engines, you have a flow path that goes into each of these three valves. So you've got three valves in the aft part of the orbiter that will cycle to provide the hydrogen in the pressurization line going to the external tank. And so you can picture you have three valves that are side by side, and they go up 5 inches to a 90-degree angle, and there's a big block of steel there that is at 90 degree. It travels about 4 more inches to another 90 degree, and then it goes down, and all three of the pipes are joined about 2 feet below that in a single manifold that goes through a disconnect valve that separates when we separate the orbiter from the external tank. And then that runs up 79 feet up the external tank, makes a small bend into the middle of the tank, and then makes a sharp bend down into the top of the hydrogen tank. What we're worried about is the tank is pretty robust, and it's although it has a 79-foot run where the particle can go, it makes a 60-degree turn, which kind of slows it down. And then it goes through these fairly massive flex joints that we call they're Bistra joints, and I'm not going to remember what the acronym stands for, but they're pretty massive, and for the particle to actually get through them is hard to believe. We didn't even put those in the test rig. We just flew the particles at Stennis Space Center up through that 60 degree and then down, and we had really very little damage at all. The area of bigger concern is in the orbiter aft part, and the biggest area of concern is 5 inches away from the poppet itself, that first 90-degree bend. And it's because when the poppet breaks off, you get a fairly instantaneous, very fast flow coming from that broken area that will accelerate that particle into that 90-degree, and it's really just a flat hit. And that is our area of least margin, and that's the one that we're going to concentrate on over the next week.